Hey everyone, welcome back to Real Analysis 1. This will be lecture 10 of the course. And in this section, we're going to switch gears a little bit and develop some more machinery that we'll need for our later discussion of differentiation. And we're going to begin talking about the structure of point sets. And we're going to start with discussing with some rigor what we mean when we talk about an open set or a closed set. And so really, you can kind of think of the next 3 lectures as being kind of the real analysis version of Introduction to Topology. So let's go ahead and jump into it. And we'll call this section 3.1, Open and Closed Sets. And so what we're interested in doing with this section is characterizing, well, defining with some amount of rigor and then characterizing what we mean by open and closed sets. So we've seen open sets and closed sets before, but here we want to develop more rigor, right, around these concepts. Right, so specifically we know what we mean when we talk about an open subset like A to B. This is, well, we've talked about in terms of an open interval, right? And then we know that a closed interval AB looks more like, we denote it anyways like this. So this is probably the extent of your experience with the idea of open and closed sets, is really just this interval concept from, elementary algebra. It certainly comes up in calculus a lot. But what happens if we're not talking about an interval as our set? What if we've got something else as our set, not necessarily just an interval? Well, in order to characterize those types of sets, we need a different way of thinking about it. And so the first concept that we really need is what's called an interior point. Okay, so let's define that. So we'll let E be a subset of R. So we're just talking about real numbers here. Obviously, this is real analysis. Let E be a subset of real numbers. Then we say a point P that's inside the set E is an interior point, interior meaning inside point. It's an interior point of E if there exists some epsilon greater than 0 such that the epsilon neighborhood of P is entirely inside of E, is a subset of E. Okay, now remember what these epsilon neighborhoods are. Let's recall that in case we can't remember. An epsilon neighborhood of P is just all of the elements, all of the real numbers x, such that x is inside of P minus E, comma P plus E. So here we are talking about an interval. An epsilon neighborhood is basically an arbitrarily small interval surrounding a number. Okay. And so an interior point is a point where it's possible to create an interval about the point such that you stay within the set E. Okay, so like if we were to try to draw a picture of this, maybe this is my set E, right, and P is in here. Well, this is an interior point because I can just create an interval. All right, so that's definitely an interior point, assuming E is just this, this entire interval. Now, it obviously becomes more tricky if E is not an interval. Another example where you would have maybe a problem would be on the endpoints here, right? So if I'm talking about the endpoint, right, if E is again this interval, and this is my P, well, if it's an endpoint, then that can't be an interior point. P is an interior point here. P is not an interior point, right, in this case. Right, specifically because, look, there's no way to make epsilon small enough such that I can draw an interval or think of an interval that is inside of E, right? Specifically right here, I got a problem, don't I? Got a little gap there. Okay, so that's what we mean by an interior point. It's just a point, that is located relative to a set such that you can create an interval, small enough interval, such that the entire neighborhood of that interval is inside the subset. Okay, let's see. So that's just kind of a drawing example. Let's see a more concrete example. Consider the set of irrational real numbers. So let's let E equal the set of reals where we've removed the rationals. So this is the irrational reals. Okay, now previously we saw that the rational numbers were dense in the real numbers, right? We saw that. So by theorem, previously, you have to go back a couple lectures, maybe 5 lectures or 6 maybe. Previously we saw that for P for P in this set E, for all epsilon greater than 0, there exists some number R that's inside of Q and the epsilon neighborhood of P, right? And that we characterize that. This is just this statement that the rational numbers are dense in the reals. So i.e. the rational numbers are dense in the real numbers. Right, meaning it's not possible, so given any P, it's not possible for you to give me an epsilon where there doesn't exist some rational number within the epsilon neighborhood of any P, right? Right, so meaning that no matter how tight of an area you look at, and no matter how small of an area you look at, you're always going to have rational numbers there. That's what it means for the rational numbers to be dense in E, right? And so this being the case, we would say therefore, the epsilon neighborhood of P always contains a point of R that is not in E. Always contains a point of R that is not in E. Right? So if P is in E, then it's irrational, right? And we know by this previous statement then that any epsilon neighborhood of an irrational number will contain a rational number. Okay. Right? So if P is an irrational number, then any epsilon neighborhood of P is going to contain a rational number. Right? So if P is in R minus Q, then any epsilon neighborhood of P will contain elements of Q, right? Will contain a rational number. And given this, there are no interior points of E. There are no interior points of E, right? So there's no interior points of the irrational reals, right? There's no way to create a small enough interval such that I'm inside of the irrational numbers alone. There's no way to isolate a subset of irrational reals via an interval. Okay, so that's kind of a more complex example, but it shows you the power of this idea of interior points, right? Okay, very good. Let's keep cruising. Here's another example, maybe a more straightforward example. I like that previous example, but it's not great for developing a picture of these things. And I think examples should do that as well. It is good to look at complicated examples, obviously, but sometimes you just want something a little simpler. Well, let's let E equal this interval A to B, right? So then if P is in E, if P is some number in this set E, P is an interior point. Okay. If P is in E, then P is an interior point. Well, is it always an interior point? We'll say most of the time. Right, but let's think about what this looks like here. So here I've got my lower endpoint. Here I've got my upper endpoint. So my A is down here and my B is up here. Right, so most of the time I can think of P as just being like this, and then this is P minus epsilon, and that's P plus epsilon. And this is the neighborhood of P, the epsilon neighborhood of P. And we can easily see that the epsilon neighborhood of P is going to be within E, right? So the epsilon neighborhood of P in this case is contained in E. Now you run into a problem on the upper end, right? Up here, if P equals B, then I've got a problem, right? Because this is B plus epsilon, this is B minus epsilon, and guess what? The epsilon neighborhood of B is definitely not a subset of E, right? And because of this section here, right? You got this piece that kind of is leaking. Okay. Right, so that would not be an interior point. Okay. All right. Excellent. Okay. Let's move forward with the definition of open and closed subsets. Okay, so definition. A subset O of R, of real numbers, is open. It's open if every point of O is an interior point. Okay, so a subset O is open if every point in O is an interior point. And so that's how we characterize an open set, and we say that a subset, we'll denote it with an F, a subset F of R is closed if its complement is open. Okay. So we really have this definition for an open set, and then if something, if a set is closed, we say that its complement must be open, right? Right, and so falling back on the examples we're familiar with, if you think about an open interval, A to B, so where here the endpoints are not part of the set, well, you can imagine that I can get as close as I want to those endpoints and still have space, right? I just can't go up to those endpoints, right? But I can get very, very close with my P's here, and I can always shrink down my epsilon so that it's small enough that I can still have an epsilon neighborhood inside the open interval. Now, when I have a closed interval, that's where we run into problems, right? If I have my A and my B over here, then it's possible for me to consider the actual point on the end. And when I have the point on the end, then there's no epsilon that's going to not produce this gap right here. Okay. So this is, this open interval idea you may remember from calculus or from talking about limit points earlier. you can never identify the number next. It basically boils down to the idea in analysis with a continuum with the real numbers. You can never identify the number that's directly next to A, right? There is no number next to A in the real numbers, right? There's just a continuum, an infinity of numbers. No matter how close to A you get, you're always dealing with an infinite number of numbers. So that's really kind of the kernel of it. And this concept of an open set really is great at getting at the reality of how dense the real numbers are. They are not discrete. It is a continuum. And this really gets at that idea. Okay. Let's see here. So let's think of a closed interval here by kind of using the definition. So given that AB is closed, let's consider its complement. So if this is AB, then the complement of this thing would be what? Well, it's going to be negative infinity up to A union with B up to positive infinity, right? So in the case of an interval, the complement of a closed interval is obviously open. Notice the endpoints here, right? And so this is obviously an open set, right? And so the idea of a closed interval can really we can fall back to the definition. A subset, an interval is closed if its complement is open, which we can clearly see would be the case. Okay. Now I don't want to dwell too much on just the idea of intervals. It's just that we have a lot of intuition when it comes to intervals because we've seen them for a long time and we know what an open interval is, we know what a closed interval is, and so all of the things we're defining now are generalizations of those concepts, right? And so we can always fall back on the idea of an interval to help develop intuition. What about a couple more examples? The real numbers are open. R is open, and this should be relatively obvious. We can say for any P in R, and well, in really any epsilon greater than 0, the epsilon neighborhood of P is again a real number. It's the epsilon neighborhood of P is a subset of R is what I meant to say there. All right, so that one should be obvious. The reals are open. Right. Another example. Here's another example. For any epsilon greater than 0, the epsilon neighborhood of P, where P is just any real number, is an open set itself, is also an open set. Right, so basically any, if I've got a point P, then the set defined by the interval P minus E up to P plus E is an open set. That might be obvious because it's an interval, open interval. All right. Right, it's just how that's defined, right? The epsilon neighborhood is defined as this. Okay. How can we show that an epsilon neighborhood is open, though? Right? We want to say that it's open because it's an interval. But how can we show this? Let's show it. How can we show this? Let's let epsilon greater than 0 be given, and let P be any real number, right? As the example says. Then if Q is in the epsilon neighborhood of P, right? If Q is in the epsilon neighborhood of P, we would say that the distance between P and Q must be less than epsilon, right? Okay. And so what we can do is we can choose delta, right? Another small Greek distance. We can choose delta greater than 0 such that delta's, 0 is less than delta, which would be less than, we could say epsilon minus whatever this distance is, P minus Q. right? So specifically, we could choose delta such that it's less than whatever the distance is between epsilon and p minus q. Okay, so then if x is in the delta neighborhood of q, we have what? Well, we'll know that x minus p, what's the distance between x and p? Well, it's going to be less than or equal to p minus q plus x minus q, right? That's just kind of throwing in the q there. Okay, and that would have to be less than p minus q plus delta, right? This is less than delta. Okay, which would have to be less than or equal to p minus q plus this piece here, epsilon minus p minus q, right, which is obviously equal to epsilon. Right, so that, I mean, basically what is this implying? It's implying that this delta neighborhood of q must be inside the epsilon neighborhood of p. Right, so the implication here is that the delta neighborhood of q, an arbitrary point in the epsilon neighborhood, is a subset of the epsilon neighborhood. Right, meaning I can find a delta such that this tiny interval around q is entirely inside this epsilon neighborhood. Right, and so therefore, right, because q is an arbitrary interior point of epsilon neighborhood of p. Is an arbitrary interior point of the epsilon neighborhood of p, which implies that epsilon neighborhood of p is open. Right, so hopefully that's clear, but here's the idea, right? So I'll just draw it. It's sometimes easier just to see this drawing. Here's p, right? Here's p minus epsilon. Here's p plus epsilon. So this is the epsilon neighborhood. I take an arbitrary q in here, right? And I can find a delta such that this guy here can be drawn. This is the delta neighborhood of q. Right? And then clearly that delta neighborhood is inside this epsilon neighborhood. This is the whole thing is the epsilon neighborhood of p. Right? And so that just means that q is an interior point and q is arbitrarily chosen, so that means every point in the epsilon neighborhood of p is an interior point, which means that epsilon neighborhood of p is open. Okay, very good. All right, that's good. Right, and it's kind of, because it's an interval, it's sort of obvious to us that it would be open. Here's a nice theorem, just kind of making what I just said very concrete. Every open interval in R is an open subset of R. Right, so we already kind of saw this. I mean, does this really need proving? I'm not sure. An interval and a subset are generally considered to be the same thing. So, I mean, an interval is a set. So, but this is a nice, a nice thing to be able to say, just to make sure that it's clear. Let's let A and B. Here we can prove it. Let's let A comma B be an open interval in R. Okay. And we'll let P be an element in AB. Okay, so we'll let P be in there. And we can choose an epsilon. Right, how are we going to choose our epsilon? Well, it has to be greater than 0, so 0 is less than epsilon, which needs to be less than, and I'm going to suggest this one, the minimum of the distance between P and A, and the distance between B and P. What the heck am I doing here? Well, let's think about what we got going here. So here's my A, here's my B, P is somewhere in here. Right, so I can choose my epsilon such that it's less than the minimum of this distance or this distance, whichever one's smaller, say this one is obviously smaller, I can just choose that right there. And from that, you can see that P would have to be an interior point of A and B. So the epsilon neighborhood of P would be contained in AB, which implies that P is an interior point. Right now, obviously, if I'm really, really close to A, I just choose a smaller interval. Right? It's always possible to choose a smaller epsilon. Okay, that's the end of the proof. Pretty straightforward. Pretty straightforward. Right? So that is, this kind of cleans up, like, the idea we kind of came into the session was that intervals are subsets, and open intervals and open sets have this thing in common. It turns out that every open interval is also an open set. So now we've kind of shown that, not just waved our hands at it. Let's take a look at another theorem. What happens when you start taking unions of open sets and intersections of open sets? So here's a theorem. It's going to be kind of two parts. I'll just denote them as 1 and 2. For any collection, and I'm going to write it like this, O sub alpha, where alpha is in some index set. So for any collection of open subsets of R, for any collection of open subsets of R, the union, so union of alpha in A of O alpha, so the union of all of these subsets is open. Okay, so if I have this could be an infinite collection of open subsets. If I have a bunch of open subsets and I take the union of those subsets, then that union is open. Okay, and in the second part it says for any finite being different. This is different from the previous example. This one can be infinite. This one requires that the collection be finite. For any finite collection, and so we'll denote it as O sub 1, O sub 2, O sub n. So for any finite collection, O sub 1 through O sub n, of open subsets, so for any finite collection of open subsets of R, the intersection is open. Okay, so the intersection, which would be, kind of think of like this, I equals 1 to n of OI. So this is open. Now it's important that you notice when we're talking about the intersection of open sets, the collection has to be finite. When we're talking about the union of open sets, then the collection could be finite or infinite. Okay. All right, so this is a nice theorem, and let's prove it. We won't prove both parts just in the interest of time, but we'll prove, we'll prove that the finite intersection is open. So I equals 1 to n of OI is open. Okay. All right, so this is the one we'll focus on, this one. And so how are we going to do this? Well, let's think about what this scenario looks like here. So these are intersections, right? So let's just, this isn't necessarily how it would look, but let's draw a picture just so we can get some intuition. So maybe I've got my O1 is this interval, right? And again, we're kind of falling back on intervals just to develop intuition. And then I've got my O2, which is like this other interval, and then my O3, and then all the way down to O sub n, right? And so what's the intersection here? Well, it's just this little piece here. This is the intersection of I equals 1 to n of OI. It's just this piece here that we're interested in. All right, so what this theorem is saying is that if all of these intervals are open, then the intersection of all of them must be open. Okay, so let's. This proof is very straightforward if you have this schematic in mind. Right, so let's assume that P is inside the intersection of these open sets. Okay. Now, the way we're going to do this is we're just going to say, well, since O1 is open, there exists an epsilon 1 greater than 0 such that the epsilon 1 neighborhood of P is in O1. Right, so it's possible for, obviously this is O1, right? The big set on the outside is O1. Well, it's possible for me to create an epsilon such that, to come up with an epsilon, and P is in here, right? P is way down here. It's possible for me to come up with an epsilon such that I'm inside of O1, no problem. And we can do this again. Since O2 is open, there exists epsilon 2 greater than 0 such that the epsilon 2 neighborhood of P is in O2. Right? And if it's in O2, it's automatically in O1 also, based on our schematic. That doesn't necessarily have to play out that way, though. Okay, and this can continue on indefinitely. Now, since ON is open, there exists epsilon n greater than 0 such that the epsilon n neighborhood of P is contained in O sub n. Now remember, P is in all of these, right? So we know that we can just kind of shrink down this epsilon neighborhood until we've got basically a neighborhood that's small enough that it fits inside of everything, right? And so what that amounts to is basically we want to choose epsilon equal to the minimum of all of these. Epsilon 1, epsilon 2, dot, 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 epsilon n, right? And if that happens, then I'm definitely inside of O1, I'm definitely inside of O2, I'm inside of O3, dot, 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 I'm inside of ON, if I choose the smallest possible epsilon of this list, right? I can just come up with this list. And so that would mean that my epsilon neighborhood of P is going to be inside of O1, it's going to also be inside of O2, it's going to also be inside of ON, and another, oh, sorry, these should be the other direction, sorry about that. It's going to be inside of O1 and O2 and dot, 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 and ON, right? So it's going to be inside the intersection. Okay, so that's the proof. It's relatively straightforward, especially if you have the picture in mind. You got to remember P is by assumption inside of all of these sets. You just got to shrink down the epsilon neighborhood until you are inside of all of them. All right, perfect. Okay, and then we have another theorem that is very sort of similar. It's just the same idea: intersections and unions of closed sets. Okay, so let's take a look at what that one says. So for any collection, well, again, two parts, 1 and 2. First part says for any collection, and here we've got F sub alpha, alpha in some index set A, of closed subsets of real numbers. The intersection is closed. Okay, so I've got a potentially infinite collection of closed subsets, then that the intersection of all of those closed subsets must also be closed. All right, and then part 2 is says for any finite collection, and we'll denote it F sub 1, F sub 2, dot, 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 F sub n of closed subsets of R. The union alpha equals 1 to n of those guys is closed also. Okay. So when we were talking about open subsets, we could have an infinite collection in a union, and we could have a finite collection in an intersection. Now here it's reversed. So here we're talking about closed subsets, so the intersection can be infinite and the union has to be finite. All right, so it's just an important thing to note. right? That those are reversed. And so we can, again, we'll prove this. We'll prove just one of them. We'll prove that, we'll show that the union I equals 1 to n of f sub I is closed. Right, now how do we do that? Do we remember the definition of a closed set? Right? What's the definition? Well, it's the complement is open, right? So to show, let me just write this down, to show that the union I equals 1 to n of f sub I is closed, we need to show that the complement of this is open. And that can be, well, let's just see what happens. I mean, you see this notation, you kind of know what's coming, right? We're going to expand this thing, right? We're going to expand this thing. And so let's take a look at that. So if I have the union of I equals 1 to n of f sub I complement, I know that that's equal to f1 complement and f2 complement and dot 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 and fn complement, right? So this is going back to your set operations, some kind of earlier set theory stuff from the class, right? So this is an intersection of finitely many sets, right? There's n of them, right? Now notice f1 is closed, and that implies that f1 complement is open. And I'll just say fi, really. For each of these, the assumption is that f sub I is closed, and therefore its complement must be open. So what are we talking about here? What is this? This is an intersection of finitely many open sets. This is, so f sub 1 and complement and dot 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 and f sub n complement is an intersection of finitely many open sets. And the implication there is that obviously the intersection is open by the previous theorem, right? Right, so if this is an open set, then the intersection is also open, right? And so that's basically the proof, right? So if the union from I equals 1 to n of f sub I complement is open, then the union from I equals 1 to n of f sub I is closed. Right, and so that's the proof. We just need to be sure that the collection is finite. Right, so this wouldn't be true if this was an infinite set. Right, there are counterexamples. Right, we're going to see one in a second here, but the fact that we're talking about a finite collection of closed sets means we can just expand this and use the previous theorem. Okay, and I'll leave the other one for you guys to prove. You can just take a couple minutes and you can probably figure it out. It's similar. Let's do an example. This is a good example. Let's let O sub n, this is an open set, let's let it equal this interval, negative 1 over n to 1 over n. Right? This is an open interval, as you can see, so it's an open set. So each O sub n is an open set. But let's see what happens when we try to take the infinite intersection of this. So what happens with this thing? I equals 1 to infinity of O sub I. What happens with this? Well, what is this thing? Okay, let's look. I equals 1 to infinity of O sub I. What is it? It's, well, when I is 1, it's negative 1 to 1. Right, and this is an intersection, so we need to intersect that with what happens, these set I equals 2, so that would be negative 1/2 to 1/2. We need to intersect that with negative 1/3 to 1/3, and so on to infinity, right? So what is going on here? Well, if this is -1 and this is +1, well, it's just going to do this, isn't it? Right in the middle is 0. Right? It's just going to keep getting smaller and smaller and smaller and smaller and smaller and smaller. And so ultimately, what is this intersection equal to? What's the only thing that is in? Well, you could think about it like this: when the denominator goes to infinity, what does this number go to? 1 divided by something insanely large is very close to 0. So really, conceptually speaking, the center here, the intersection, is just the number 0. Right? So the intersection is a single number, and obviously a single number cannot be an interior point, right? So it's not open. So here, the intersection is a single point and cannot therefore be open. Okay, so that's a nice little example of why the intersection of open sets has to be a finite number of them. This would be a counterexample. All right, very good. Very good. I think I'm going to break this lecture up into 2 parts. And so when we come back, we'll continue on with part B. So this will be the end of part A, and in part B we'll continue with our characterization of open and closed sets.